Welcome to the Explainer. Today, we're going to tackle a system design interview question that seems super simple on the surface, but oh man, it is packed with interesting challenges. We're designing a parking lot management system from scratch. I mean, how hard can it be, right? A car comes in, a car goes out, you take a ticket, you pay. Seems easy enough. But as you'll see, this problem is actually a fantastic way for an interviewer to test how you handle real-world complexity and if you can think like a real system architect. You know, this problem is a total iceberg. On the surface, it's just parking cars, but underneath, an interviewer can probe your knowledge of scalability, concurrency, payments, fault tolerance, pretty much the whole shebang. So stick with me, and by the end of this, you're going to have a rock-solid framework to absolutely nail this question. All right, let's dive in. We're going to walk through this exactly how you should in a real interview. We'll start by clarifying the problem, then we'll sketch out the big picture design, figure out our data model, do a deep dive into the trickiest part, the entry flow, and wrap up by talking about how to make sure this thing can scale. First things first, let's really understand the problem. Okay, this first step is absolutely crucial. This is where you prove to the interviewer that you're a systematic thinker. Before we even dream of writing code or picking a database, we have to know exactly what it is we're building. So let's figure out what's really going on here. Let's set the stage. We're not just talking about some tiny 20-car lot. Imagine a big, multi-story parking garage, maybe at an airport or a shopping mall. It's got multiple entrances, multiple exits, and right away, that introduces a fun little bit of complexity. How do you coordinate all of that at once? Here's a pro tip for basically any system design interview. Split your requirements into two buckets. First, you've got your functional requirements. That's the what. What does the system actually have to do? Then you've got your non-functional requirements. That's the how well. How fast does it need to be? How reliable? How big can it get? So for our functional side, let's think about the journey of a car. Our system needs to handle all kinds of vehicles, motorcycles, cars, big trucks, you name it. It has to know about different spot types, like compact or handicapped. It's got to issue a ticket at the gate, figure out the fee, process payments, and this is a big one, show drivers where to go with real-time display boards. Now for the non-functionals. This is where things get serious. The system has to be, well, bulletproof. It needs high availability. Can you imagine the chaos if this thing went down at 5 p.m. on a Friday? No way. It has to be super reliable. We can't ever double book a spot or lose a payment record. And of course, it needs to be fast to keep traffic moving and scalable enough to grow. All right, requirements are locked in. Now it's time to zoom out and get that 30,000-foot view. We're going to sketch out the main pieces of our system and see how they all fit together. Think of this as our architectural blueprint. We're going to go with a microservices architecture here. So out in the real world, we have the physical entry and exit gates. Those gates talk to our back-end services. We'll have a slot management service. This is the brain of the whole operation. It knows where every single spot is and if it's free. We'll have a ticketing service to create and track tickets, and a payment service to handle the money. It's all backed by a central database, and we'll have an admin dashboard so a human can see what's going on. Now, this flow is so important. It shows how a real-world action, a car pulling up, kicks off a very specific chain of events in our system. The car arrives, the gate pings the slot management service to find and reserve a spot, then the ticketing service jumps in and creates a new ticket. Only when all of that succeeds does the gate finally open. Getting the sequence perfect is the key to a reliable system. All right, let's dig into the foundation of our entire system, the data. How we model our data, and especially the type of database we choose, is going to have a huge impact on our performance, our reliability, and our ability to avoid those catastrophic errors like double booking a spot. So let's start with the basics. What are the main things in our system? We can call these our data entities. Well, we've got a vehicle, we've got a parking spot, we have a parking ticket, which links a vehicle to a spot, and of course, a payment record. Thinking about it this way, like objects, makes it way easier to design our database schema. Let's zoom in on just one of these, the parking spot table. Each spot is going to need a unique ID, what floor it's on, what type of spot it is, and here's the most important part, an is available flag. Now, here's a little performance secret. You definitely want to put a database index on that is available column. Why? So that when we need to find an empty spot, which is going to happen all the time, the search is lightning fast. Okay, big decision time. SQL or no SQL? No SQL databases are really popular for their speed and scale, and that's tempting. But the absolute heart of the system is about transactions and consistency. The one thing we cannot let happen is double booking a spot. And for that reason, a good old-fashioned relational SQL database is the clear winner. Its support for something called ACID transactions gives us the strong consistency we need to keep our data safe.
All right, this is it. This is the part of the interview where you can really separate yourself from the pack. We are going to dive into the single trickiest part of this whole system, concurrency. What happens when two cars try to do the same thing at the exact same time? So here's the classic question an interviewer might throw at you. Okay, there's exactly one spot left in the entire garage. Two cars drive up to two different entrances at the exact same millisecond. What happens? This is a textbook setup for a really nasty problem in computer science called a race condition. If we don't handle this carefully, our system would just break. The request from car A checks the database and says, yep, one spot free. But before it can write back and claim it, the request from car B also checks and sees, yep, one spot free. Now they both think they can assign that spot. And boom, we've got two cars assigned to the same spot, our data is corrupt, and we've got a very angry customer. It's a disaster.
And this, my friends, is exactly why we chose that SQL database. The solution is something called a database transaction. We basically wrap the check for a free spot step and the reserve that spot step into a single all-or-nothing operation. You can think of it like putting a lock on that spot in the database. Once car A's request starts that transaction, car B's request has to wait in line until car A is completely finished. This gives us a guarantee that we will never, ever double book.
Okay, so our design works, it's consistent, it's safe. But what happens when we're running not just one garage, but a whole city's worth, or a giant airport that's open 24/7? Now we need to talk about scaling and reliability.
To handle massive traffic, we'll use some standard battle-tested patterns. We'll stick a load balancer out front to spread requests evenly. We'll use horizontal scaling, which is just a fancy way of saying we can add more servers whenever we need to. For the database, we'll use a primary replica setup. All the writes, like making a reservation, go to the primary database. All the reads, like just checking for spots, can go to multiple copies or replicas. This splits up the work. And finally, we have to plan for failure. What if the payment system goes down? We can switch to a simple cash-only mode so cars can still get out. That's called graceful degradation. In any system design interview, talking about trade-offs is what really shows your seniority. We made some very deliberate choices here. We chose strong consistency over maybe slightly higher performance because for a parking lot, correctness is everything. We chose SQL because of its transaction support. And we chose microservices so that we could scale our payment service and our slot management service totally independently, because they'll have very different traffic patterns.
So, to wrap it all up, here's your interview playbook. Number 1, always start by clarifying requirements. Ask questions. Number 2, start with the high-level design first, the big picture. Number 3, pick one complex area, like that race condition we talked about, and go deep to show you know your stuff. And finally, number 4, always talk about the trade-offs. Explaining the why behind your choices shows that you're not just designing, you're engineering.
So there you have it. You can see how a question that sounds so simple on the surface really pushes you to think like a complete systems architect. By following this kind of structured approach, you can break down any big problem into a clean, robust design. Now that we have this solid foundation, what would you build on top of it? Maybe a system to reserve spots in advance, or pricing that changes with demand. How about integrating EV charging stations? The possibilities are pretty much endless. Thanks for joining me on The Explainer.